Kuzuzangpo, Bhutan e-learning project welcomes children to this lesson. I'm Dam Chuangchu. This is a physics lesson for Key Stage 5 classes 11 and 12. In this lesson, you will learn about mass defect and binding energy. And you will also learn about the nuclear reactions like nuclear fusion and nuclear fission, regulating the particles, and the radioactive decay. Particle physics is the branch of physics that deals with the property, the relationships, and the interaction of subatomic particles that makes up all the matter in this universe. We know that size of the nucleus is very small as compared to the size of the atom, but it contains most of the mass of an atom. A tiny central core in which the entire positive charge and almost entire mass of the atoms are concentrated is known as nucleus. The energy emitted by those nucleus as it becomes more stable is called nuclear energy. The difference in mass of constituent nucleon and the mass of nucleus is known as mass defect and is denoted by delta M. The mass defect delta M is calculated by the given formula here. Mp, Mn and M nucleus are the mass of proton, neutron and the nucleus respectively. The nucleons are bounded together in a nucleus, and the energy that has to be supplied in order to break apart the constituents into free nucleon is called binding energy. It is denoted by capital letter Be. Most of the time, binding energy is calculated in mega electron volt. Let us discuss more in detail with some examples. In this case, we have 4 protons and 3 neutrons, and adding the individual masses, we'll get the mass of constituent nucleon Mb. If we put them in nucleus, we will have beryllium because of its atomic number 4. The mass of a nucleus is denoted by Ma, where mass of a constituent nucleon is greater than mass of a nucleus. The difference between two masses is the mass defect, which we can convert it into binding energy. Let us look at another example. Imagine this nucleus with 2 protons and 2 neutrons. It is helium, and if you want to split this nucleus into constituent nucleon, we need to apply a force to each particle which is bounded together by a strong nuclear force. Since work done is equal to the product of force and distance, adding force means supplying energy. The energy is used to break the nucleus into constituent nucleons. Therefore, binding energy is the energy required to split the nucleons apart. According to the Einstein's equation, E is equals to mc square. The supply in energy means supply in mass. If we place these two on imaginary weighing machine, you can see that the constituent nucleon is much heavier due to excess mass obtained through energy. Thus, we can calculate mass defect and binding energy. Let us try to determine the mass defect and average binding energy per nucleon for iron 56 nucleus. The mass of a proton is 1.007825 atomic mass unit and the mass of neutron is 1.008665 atomic mass unit. So the atomic number for the iron is 26. So therefore the mass of a proton times atomic number is 26.203450 atomic mass unit, and likewise the difference of atomic mass and atomic number is 30. So when we multiply it with the mass of a neutron, we are getting 30.25995 0.50 atomic mass unit. When we add it, we get 56.463400 atomic mass unit, which is the mass of a constituent nucleon. The given mass of iron is 55.934939. So subtracting this two, we will get the mass defect, which is equal to 0.528461 atomic mass unit U. Using the equation E is equals to mc square, we can convert the mass defect to energy. So for that, the mass need to be in kilogram. So we know that 1 atomic mass unit is equals to 1.66 times 10 raised to negative 27 kg. So where the mass defect, we will get it as 8.77 times 10 raised to negative 28 kg. Now using E is equals to mc square, where 8.77 times 10 raised to power negative 28 times the speed of light square. So we will get E is equals to 7.89 times 10 raised to power negative 11 joules. The binding energy is always expressed in electron volt. So 1 electron volt is equals to 1.6 times 10 raised to power negative 19 joules, from where we'll get binding energy is equals to 493 times 10 raised to power 6 electron volt. As discussed earlier, the binding energy is expressed in mega electron volt. So 10 raised to power 6 electron volt is equals to 1 mega electron volt, from where we can say that binding energy is 493 mega electron volt. As per the question, you are asked to calculate the binding energy per nucleon. Therefore, iron having 56 nucleons, so we just need to divide the binding energy by 56, where we get 8.812 mega electron volt. Binding energy per nucleon is very useful quantity in predicting the stability of a nucleus. In a figure, binding energy per nucleon versus mass number A is shown. Binding energy per nucleon reaches maximum of about 8.7 mega electron volt for mass number A between 50 to 80. This is called the region of greatest stability. Those nuclei whose mass number A lies above and below the stability region are considered as less stable, which will undergo the nuclear reaction. When a nucleus is formed, nucleon emits light. When light is being emitted, nucleon loses mass. This is because energy is equivalent to mass. When we have a small nucleus, each nucleon loses less energy, and when we have a bigger nucleus, each nucleon loses more energy. We can name this nuclei as hydrogen 2, helium 3 and helium 4. Let's plot the trend. Bigger nucleus loses more energy per nucleon. By using a graph, let us discuss the concept. On x-axis, it shows the size of a nucleus, and on y-axis, it shows how much energy each nucleon loses. The graph shows increase in its initial phases as we discussed. Let us take 3 different nuclei, and we are going to put 3 different nucleons nearby. This nuclei acts like a magnet, but they don't pull with the magnetic force, rather pulls with the nuclear force. So the smaller the nucleus, weaker the force, and bigger the nucleus, greater the force. Which of the three nucleons have least potential energy? The nucleons experiencing least force will have least potential energy. Let us assume that they have potential energy of 3 electron volt and 7 electron volt respectively. When the nucleon meets the small nucleus, it loses less potential energy. Whereas when the nucleon meets the bigger nucleus, it loses more potential energy, therefore loses more mass. But remember, this concept can be applied particularly to those atoms having mass number less than 50. If we take a huge nucleus and put a nucleon close by, does it act like a huge magnet to the nucleon with a giant force? The answer is no. The number of protons inside the huge nucleus will act against the nuclear force. The distant proton will experience the repulsive force, which makes the nuclear force very weak. When we compare the bigger nucleus and the medium nucleus acts like a bigger magnet, and each nucleon loses more energy as compared to the bigger nucleus. Let us look at the graph. This region is known as the region of stability. Now, when the atomic mass increases, you can see out here the energy released per nucleon keeps on increasing till it reaches the stability region. Beyond it, even when we increase the atomic mass, the energy released per nucleon decreases. That is why when we look at the binding energy curve, we can see that initially atom loses more energy and then suddenly drops. So the nucleus undergo the reaction to obtain the stability. Earlier in this lesson, we have found that the average binding energy per nucleon for an iron 56 nucleus is about 8.812 mega electron volt. When we look at the binding energy curve, we can see that the iron lies in the region of greatest stability, which indicates that the nucleus of iron 56 is stable. Let us look at two types of atomic reaction: nuclear fusion and nuclear fission. Nuclear fission. In this process, atomic nucleus is hit by a single neutron that is flying around. The impact causes the atomic nucleus to split into two new nuclei. Each of them takes part of electrons with them so that two new atoms are formed. In case of some very large atoms, few neutrons are additionally released. When uranium atoms are split in a nuclear plant, this usually involves release of 3 neutrons. This can affect the next fission processes in a chain reaction. Finally, the energy is released. 1 kg of naturally occurring uranium has energy of 12,000 liters of mineral oil, or almost 19,000 kg of hard coal. Where does this energy come from? Why is it so much more than the case of other energy carrier? Let us recall. Beside the neutrons, the atomic nucleus only consists of the positively charged protons. Now equal charges repel each other, but the proton in atomic nucleus always remain together due to the strong interaction, which is known as strong nuclear force. It acts like a strong rubber band that holds atomic nucleus with its proton together. When impacting neutrons force the nucleus apart. It is exactly the energy that has been stored in the rubber that is released. Pros and cons of nuclear fission. The nuclear reactor forces the atoms of uranium to break apart. As they split, the atoms release tiny particles called fission product. Fission product causes other uranium atoms to split, starting a chain reaction. The energy released from this chain reaction creates heat. The heat created by the nuclear fusion warms a cooling agent, usually water. The cooling agent produces steam that runs turbines. The turbines drive generators or engine that creates electricity. Nuclear energy can provide clean, pollution-free power with no greenhouse gas emission and deforestation. However, nuclear reactors do produce radioactive waste that are extremely toxic. Harmful radiation stays for thousands of years, causing the harmful effect to the living beings. Nuclear fusion. Nuclear fusion works only with smaller atoms like hydrogen. The atomic nucleus of hydrogen consists of only one proton. If you try to bring these two protons together, they will repel each other due to like charges. This is referred as a Coulomb's force. This force acts as if each of the protons had a fence around them trying to keep off other protons. Like fission needing a force to overcome the rubber band of strong interaction, fusion also needs one that the forces of protons so closely together that the forces are pulled down. And once this happens, a proton comes too closely together, strong interaction comes into play and make sure that two protons can make one new atomic nucleus. In case of nuclear fusion on the Sun, it is in fact 4 hydrogen atoms, that means 4 protons combination can make a helium atom. In the process, large amount of energy is released. In this case, it just needs 1 gram of hydrogen isotope to gain energy of 12,000 kg of hard quartz. Just imagine if you can generate 12 kilovolt of electricity from 10 gram of hydrogen isotopes using the process of nuclear fusion. For how long will it last? Look at the similarities and the differences between two nuclear reactions. Based on the lesson which you have learned today, solve the following questions. Question number 1. Uranium-235 disintegrates as follows. Uranium-235 is equals to cerium-140 plus zirconium-94 plus neutron. Find the energy released in this reaction. Question number 2. What safety measures a nuclear engineer must consider while designing a nuclear reactor? Question number 3. Would you recommend a nuclear reaction as an alternative source of energy in Bhutan? Why? Thank you for attending this lesson. I'll see you all in my next lesson. Thank you and Karinche.